Welcome back to the deep dive. Today, we're taking on a pretty specialized mission, really plunging deep into that frontier where thermodynamics meets the quantum world.
Hmm.
We're moving way past the comfortable classical rules,
Mhm.
the ones for big machines where you can sort of treat systems and environments like they're totally separate things.
Yeah, that whole classical view,
Right.
it dissolves when you get down to the nanoscale. The moment your system shrinks, strong coupling, finite baths, quantum correlations like entanglement, they're not just possibilities, they're basically unavoidable.
Right.
And these aren't just small complications. They fundamentally, invalidate the standard second law as we usually think about it.
So our goal today is really technical clarity. We're aiming to synthesize this generalized framework, the one largely laid out by Aguilar and Lutz. It promises, well, it delivers a unified set of thermodynamic laws for these correlated quantum systems.
And we need to connect that theory, that abstract math, to the real world.
Exactly. We'll look at the experimental evidence, too. Specifically, Peterson and colleagues' work characterizing a spin quantum auto engine. The goal is to show that these non-classical resources, they aren't just theoretical quirks.
No, they're actual quantifiable fuel,
Yeah.
something that can genuinely change engine performance, maybe even, push past the famous Carnot limit.
Yeah, potentially.
So we should treat this as a foundational briefing, really. The theory paper gives us the exact mathematical tools, how to define work, how to define entropy when correlations are everywhere.
And the experiment.
The experiment shows the practical side, the challenges of finite time operation, this thing called quantum friction.
Yeah.
It really highlights the limits in real devices. So yeah, prepare for a deep dive into the actual mechanisms.
Yeah.
It's not just about efficiency numbers. It's kind of redefining energy conversion itself.
Okay, let's start by grounding ourselves. Remind everyone about that classical constraint, the one from the standard second law that dominated for so long.
Right. That law, it basically says the absolute maximum efficiency, teller, for any heat engine working between two thermal baths is the Carnot efficiency. Eneller, teller equal 1 TCH dou. Simple, elegant,
But built on a huge assumption.
a non-negotiable one, really.
Yeah.
It assumes the working system and the thermal baths are completely uncorrelated while the engine runs.
And for big classical engines, that assumption holds up pretty well, doesn't it?
It does, totally justified.
Yeah.
If you've got a massive system, its internal energy, the stuff doing the work scales with the volume. But the energy tied up in the interaction, the coupling between the system and the bath, that typically scales only with the surface area.
Ah, the volume versus surface area argument.
Exactly. Volume grows much faster than surface area as things get bigger.
Yeah.
So in that thermodynamic limit, the interaction energy just becomes, well, negligible compared to the internal energy.
Weak coupling, suppressed correlations. Standard thermodynamics works.
Precisely.
But then we shrink down. The microscopic, the quantum realm, it just flips that whole calculation, doesn't it?
Completely. Surface to volume ratio doesn't help anymore. The interaction energy isn't suppressed. You're in a strong coupling regime. The system and its reservoirs get, intimately linked.
And that linkage shows up as quantum correlations, like entanglement.
Exactly. Entanglement, other quantum correlations. They radically violate that core, uncorrelated assumption. And this isn't like a small tweak we need to make. It forces us to generalize the entire thermodynamic framework.
We need to account for energy and information flowing because of correlation, not just heat flowing in the classical sense.
And people tried before, right? Using information theory or Hamiltonian of mean force approaches.
Yeah, but they were sort of limited, weren't they? Maybe they could handle system bath entanglement, but not the whole picture.
Right. They lacked a truly unified structure.
Yeah.
And that's critical. You need a framework that can handle all the correlations inside the working system itself.
Like between coupled qubits in the engine.
Exactly. And correlations between the system and potentially many different baths, and even correlations among the baths themselves. That last one sounds weird, but it matters at this scale.
Without that complete picture, you can't really pin down the total work potential accurately.
Nope. And that brings us to the big shift in thinking. These quantum effects, coherence, entanglement, even just classical correlations built up over time, they're not just complications or noise. They're potential resources, quantifiable ones.
We had hints of this before, didn't we? Some early work showing correlations could maybe reverse heat flow or maybe boost efficiency beyond Carnot in very specific idealized cases.
Yeah, there were hints. But this generalized framework, it kind of gives us the universal mathematical okay to really go after this systematically, to treat these effects as fuel.
Okay, so let's dig into that generalized framework from Aguilar and Lutz. How does it extend the first and second laws for these, complex quantum scenarios? We've got a system math call interacting with reservoirs, math call RJ.
All right, the generalized first law. It starts with the total Hamiltonian HNTT.
Oh.
And this thing is complicated. It's got the system parts, the bath parts, and these time-dependent interaction terms of RedGT. Those interactions have to be time-dependent because we're driving the engine, changing couplings.
The big challenge classically is defining work when the system and bath are strongly interacting. How do you split up that interaction energy? How does this formalism get around that?
It uses a really clever trick based on the Ehrenfest theorem.
Mm-hmm.
Work, dollars, is defined by looking at how the total Hamiltonian changes in time due to external driving. So partial Nangle BHT DTRT dollars dollar.
So you calculate work from the perspective of what the external agent is doing to the whole thing.
Exactly. And by doing that, you completely sidestep the messy question of whose energy is the interaction energy.
Mm.
You don't need to partition it.
That's neat. So that leads to the generalized energy balance. $1 AT, QJJ plus delta U1. 2 dollars is heat from reservoir J. What about delta U1? That's the change in energy of the whole compound system.
Yes, the compound system, explicitly including that interaction energy. And here's where things get really non-classical about cycles.
Right. Classically, a cycle means the system ends up back where it started, so delta U has to be 0.
But not here. Even if the driving Hamiltonian high Pornia dollar is perfectly periodic, the delta U term doesn't necessarily vanish over a cycle.
Why not?
Because if you look at the system's averaged Hamiltonian high d, that average value might not be periodic. The evolution itself, the dynamics, can cause energy to accumulate in the interaction terms, or in the system's internal configuration, in a way that prevents the average energy from returning to its starting value, even if the external driving has completed a full cycle.
So delta U, which includes these interaction energy changes, can be a non-zero source or sink of energy contributing to the work over a cycle. That's fundamentally different.
Absolutely. That's a core non-classical feature.
Okay, so that's the energy bookkeeping, the first law. What about the second law? That has to deal with entropy and the limits on transformation, especially with all these correlations flying around.
Right. The key is tracking the change in von Neumann entropy for all the parts. By making sure the total evolution is unitary, which it must be for a closed system, they derive a generalized Clausius equality.
And this introduces a new term, right? Delta sigma.
Exactly. The equation looks like SUNY delta S Roy plus some J QJ KTJ delta sigma. Here, delta S Roy is the entropy change of the system parts, KJ KTJ dial is the standard Clausius term for heat exchange, and delta sigma is the change in the total non-equilibrium entropy produced during the cycle.
And this total entropy produced, sigma, this seems like the linchpin. It's got 4 distinct pieces, you said. Let's break those down. What do they physically mean?
Okay, first is the I-del. That's the mutual information between the system math pool and all the reservoirs math code together. This is pretty standard. It quantifies system-reservoir correlations, including any entanglement between them.
Makes sense. What are the Soothi Mathcal and Sethi Mathcal terms? Multivariate mutual information.
Yeah, basically extension. C-Mathcalers measures correlations within the system itself. So if your working substance is, say, 2 coupled qubits, C-Tax tracks how much coherence or entanglement exists between those qubits. That internal correlation can be built up or used up during the cycle.
So it's like an internal resource within the engine itself.
Precisely. Then TD Nathcalers is maybe the most subtle one. Correlations among the different baths. Why would baths be correlated? Well, in these microscopic systems, reservoirs aren't infinite ideals. If you have, say, 2 finite baths, and the system couples them together in some way, the overall state of the combined reservoir might become correlated.
Okay. So if you have engineered environments or just small baths that can influence each other through the system, that term captures it.
And finally, the last term, C navigator Rochely entropation. Roll come tail it down.
That measures distance between probability distributions, right?
Exactly. Here it quantifies how far the actual state of each reservoir has been pushed away from its assigned ideal thermal state. If the bath is small or interacts strongly, the system can actually knock it out of perfect thermal equilibrium. This term measures that displacement.
So sigma at the end of the cycle, sigma plus tau, represents the total irreversibility generated everywhere in the system, between system and baths, within the baths, and due to baths being non-thermal.
That's it. It's the total thermodynamic cost of running the engine for one cycle, measured in units of correlation and displacement from equilibrium. And since entropy production can't be negative, sigma itself must always be greater than or equal to 0. Sigma delete 1.
Okay, but if sigma itself has to be positive, representing the cost, where's the resource? You mentioned correlations as a resource.
The crucial point isn't sigma itself, but the change in sigma over one cycle. Delta sigma delta's tau. While the total entropy produced, sigma must be non-negative. The change from the initial state, delta sigma, can have either sign.
How can it be negative?
Well, think about the initial state. If you start the cycle with the system already in a highly correlated state, or maybe the baths are initially far from thermal equilibrium, then sigma is large and positive. You have a kind of stockpile of non-thermal order or information.
Okay.
Now, if the engine's process, the cycle, is designed specifically to reduce those pre-existing correlations, to essentially smooth out the non-equilibrium state, then the final sigma tum plus tau could be smaller than the initial sigma tum. In that case, delta sigma is negative.
So a negative delta sigma means you're consuming initial correlations or non-equilibrium features.
Exactly. You're treating those available correlations as an entropic resource. You're depleting them to get work out, just like you deplete a temperature difference in a normal heat engine.
And that explains the idea of an inverted entropy balance.
Precisely. If delta sigma $, then that whole combination, sumi delta S plus some JQJ, KTJJ, can actually be less than 0. Standard thermodynamics absolutely forbids this because it implicitly assumes sigma T starts at 0. No initial correlations.
But if you start with correlations, you can essentially extract work by destroying that stored information or coherence.
That's the core idea.
So how does this translate into efficiency? We have the generalized first law for work dollar and this delta sigma concept from the second law.
Right. Combine them and you get the generalized formula for the total work dollars. And its structure is really revealing. You can see two distinct ways energy gets turned into work.
Okay, what are they?
The formula basically looks like the delta Korea dollars kapki chi A plus ki T min delta sigma. The first part, some JPJG, that's the work you get from standard heat conversion like local Carnot cycles using the heat Ki-Chi chain day.
Standard stuff. But the second term, Ki-T min delta sigma, that's the new part.
That's the work derived from these non-thermal entropic sources. And delta sigma here is the key generalized entropy contribution. It includes not just the correlation changes, delta sigma, but also changes in the system's generalized free energy, delta phi.
Ah, that connects back to the delta U term from the first law.
Yes. Delta sigma bundles together the change in stored interaction energy via delta phi and the change in correlation entropy. For a perfectly ideal cycle where the subsystem state returns exactly delta phi dollars, then delta sigma just becomes delta sigma. So delta sigma is the ultimate measure of the total entropic resource available at the start of the cycle from correlations and non-equilibrium states.
And the efficiency bound. Does this change the Carnot limit?
It leads to a generalized efficiency into, and the upper bound becomes delta sigma, delta sigma. Here gets a total energy input, which might include heat and the system energy change.
So wait, if delta sigma is negative?
Then that second term becomes positive. It means Picta can actually be greater than the standard Carnot efficiency.
Wow.
That's the breakthrough. The engine can surpass the traditional limit if it's extracting work by harvesting these initial entropic resources, delta sigma dollars, rather than just converting heat.
But it's crucial to stress this isn't breaking the second law, right?
Absolutely not. It's an extension of the second law to systems that don't start in boring thermal equilibrium. You're still paying for the extra work, thermodynamically speaking. You're just paying by depleting this non-classical resource, delta sigma.
If you force the system back to a classical starting point, delta sigma becomes non-negative. It relates to the irreversible entropy production sigma, and you immediately recover the standard Carnot limit till delay.
Exactly. The framework smoothly connects the quantum correlated regime back to the classical one.
This framework also gives a way to distinguish between different operating modes, doesn't it? Thermal versus athermal.
Yes, it provides a precise quantitative way to tell them apart. It really boils down to comparing how much work comes from heat conversion versus how much comes from depleting these entropic resources.
So the thermal regime is what we normally think of.
Pretty much. Work is produced mainly by converting heat. Mathematically, the work from the sumdratage QJ no term dominates over the Ki-T min delta sigma term.
And the athermal regime is the new possibility.
That's the really interesting one. Work is predominantly extracted from these athermal resources. Initial correlations, interaction energy, displacement from equilibrium, basically, when you have a significantly negative delta sigma that dominates the work output.
The theory even gives conditions to guarantee you stay in the thermal regime, even if there are some small correlations.
Right, it's subtle. You need two things. First, the engine has to be mostly fueled by heat, measured by a factor gamma 12.2. Second, the thermal efficiency factor itself needs to be greater than a half.
That second condition, $12.2. That implies something about the temperatures, doesn't it? It means the hot reservoir needs to be at least twice as hot as the cold one. TTC. Why is such a specific temperature requirement just to ensure thermal operation?
It comes down to this constant thermodynamic competition. If the temperature difference is too small, even if you pump in a lot of heat, the actual work you get out from the standard heat cycle part, samjiraj kushwe, might be tiny because the efficiency factor T-Tachuri is small.
Okay.
In that situation, even a small amount of initial correlation that you manage to deplete a small negative delta sigma could actually produce more work than the weak heat cycle does. The entropic resource harvesting could dominate thermodynamically.
So you need that strong temperature contrast
Okay.
to make sure the heat conversion process is powerful enough to overwhelm any potential work you might get from depleting correlations.
Exactly. It guarantees that heat is the main driver, keeping you in the familiar thermal regime.
To make this less abstract, the researchers simulated a specific model, right? Two coupled harmonic oscillators.
Yes, a concrete example. Two oscillators, frequencies omega and kaka, acting as the working substance. Each coupled to its own bath, the Nanoscale and kaka, work was done by periodically switching the coupling strength lambda ft between the two oscillators.
And how did they get the initial correlations needed for the thermal regime? Did they start it in an entangled state?
No, actually they started it in a simple uncorrelated state, just the product of the two thermal states.
Yeah.
But here's the clever part. The process within the cycle, specifically the thermalization steps where the oscillators interact with their baths while coupled to each other, naturally builds up correlations.
So the cycle itself generates the resource for the next cycle.
Precisely. Running the engine creates the non-zero sigma needed to potentially harvest in the following cycle. It's self-fueling in a way.
What did the simulation find? Was the thermal regime common or rare?
Strikingly common. They found it dominated the parameter space they tested. Something like over 87% of the operational conditions they looked at fell into the thermal regime.
Wow. So correlation-driven effects might be the norm, not the exception for these quantum engines.
It certainly suggests that. And comparing the two regimes was very instructive. In their simulated thermal case, they set parameters, gamma 0.626299 to ensure thermal operation.
Right.
And indeed, delta sigma quickly became positive or zero. The engine didn't use any entropic resources. Its efficiency stayed below delta sigma and settled down to the standard quantum auto efficiency. It behaved just like you'd expect classically.
Okay. Now the thermal case, gamma 0.5323. Here, gamma was small, not much heat input compared to other energy changes.
Right. And here, for the first few cycles, they saw it clearly for about 6 cycles. Delta sigma became increasingly negative. The engine was actively consuming that correlation fuel built up in previous cycles.
And the efficiency.
The work output dollars was larger than just the heat conversion part. As a result, the overall efficiency dollar actually exceeded the Carnot efficiency during those initial cycles. Direct numerical proof of the principle.
But you said initial cycles. Did it last?
No. And this is crucial. The theory predicted, and the simulation showed, that this thermal advantage is transient. After those first 6 or so cycles, delta sigma flipped sign and became positive. The engine just reverted back to standard thermal operation, running at the auto efficiency dollar.
Why did the advantage disappear? What killed the negative delta sigma?
The culprit is the continuous finite time driving needed to run the cycle. When you change the Hamiltonian relatively quickly, the system can't perfectly follow the instantaneous energy levels. You get transitions between eigenstates.
Non-adiabatic effects.
Exactly. And these non-adiabatic transitions inevitably generate entropy. It's often called quantum friction.
Yeah.
It's an internal irreversibility caused by the driving itself.
So this quantum friction builds up over cycles.
Yes. It accumulates, generating positive entropy, increasing sigma pull. Eventually, this internally generated entropy production overwhelms the negative contribution from consuming the initial correlations. The friction essentially destroys the resource faster than the engine can replenish it, forcing delta sigma positive and pushing the engine back into the standard thermodynamic limits.
A fleeting advantage, then.
In this simulation, yes. And one more important check they did. They compare the full quantum calculation of the entropic term delta sigma with a classical version, using only diagonal elements, relative entropy, delta tilde sigma.
What did that show?
It showed a clear difference. The full quantum term behaved differently, proving that non-classical correlations, specifically coherence, off-diagonal elements in the density matrix, were actively contributing to the entropic resource delta sigma. It wasn't just classical correlations doing the work.
Okay, so the theory and simulation paint a compelling picture. Correlations are resources. Exceeding Carnot is possible, but quantum friction is a major practical hurdle. Let's bridge this to the lab now. The Peterson et al. Experiment using NMR.
Right. This brings the ideas into a real physical system. They implemented a quantum autocycle using nuclear magnetic resonance techniques.
What was the working substance?
The spin 12 of a carbon-13 nucleus, TKSD3, within molecules in a liquid sample. Very controllable quantum system.
And the heat baths.
The primary hot bath was actually a spin of the hydrogen nucleus in the same molecule. NMR allows for selective coupling and energy transfer between these spins.
What's crucial about the energy scales in this experiment?
It operates in a regime that's very different from macroscopic engines. The typical thermal energy scale, to $8, was comparable to the energy level spacing in the quantum system, the spin energy gaps, around 10-15 picoelectron volts.
So quantum effects aren't just small perturbations. They're on the same energy scale as the thermal effects.
Exactly. Both classical thermal fluctuations and quantum energy level structure are really important for how this engine behaves.
How did they implement the Otto cycle, specifically the work strokes, the expansion, and compression?
Those were the finite time-driven parts. They used time-varying radio frequency, RF magnetic fields, targeted at the tech spin. These fields effectively change the spin's energy gap, its Hamiltonian HCCT, linearly sweeping it between two frequencies, none 1 and none 2.
Like stretching and squeezing the energy levels.
Pretty much. They get the ratio none 1, the compression factor, $3, around 1.8. And they varied the time taken for these strokes from a very fast $100 microseconds up to $700 microseconds.
How does that compare to decoherence times?
The driving time tau was much shorter than the typical spin decoherence times in their system, which are closer to seconds. This is key. It means the driving process itself was almost perfectly unitary. Energy loss to the wider environment during the work strokes was minimal.
So if there's irreversibility, it's not coming from the environment leaking energy out.
Correct. The main source of irreversibility, the entropy production, came almost entirely from the finite time driving itself. From those non-adiabatic transitions between the instantaneous energy levels of the tech spin as its Hamiltonian changed.
So this is a direct experimental measurement of that quantum friction the simulation highlighted.
Exactly. It's the energy cost associated with driving the quantum system too fast for it to perfectly adjust. That non-adiabaticity pumps energy into the system in an uncontrolled way, generating entropy and reducing the network you can extract.
Now, measuring work in a quantum system. It's not straightforward, right? Work isn't a standard quantum observable.
No, you can't just measure a single operator. Work is related to the change in energy over a process, so they had to measure it statistically, finding the probability distribution of work values.
Wait, John, how did they actually measure that distribution?
They used a really sophisticated technique, an interferometric method. Essentially, they prepare the system, run the engine cycle, and then interfere the final state with a reference state in a way that allows them to measure the characteristic function, t to t, which is the Fourier transform of the work probability distribution.
So they measure the transform, then mathematically reconstruct the distribution piece.
That's the idea. And looking at that distribution gave them huge insights. For the fastest driving times, like tau to come TG2, they didn't just see one peak for the average work. They saw 9 distinct peaks.
9. What did they correspond to?
There was a central peak near $W, representing the part of the ensemble that evolved adiabatically. But then there were pairs of peaks symmetrically located around multiples of hypanemo plus nonce and others 2 plus. These side peaks are direct signatures of the non-adiabatic transitions. Their positions and heights quantify the probability and energy costs of the system jumping between energy levels during the drive.
Clear evidence of highly non-adiabatic operation and the quantum friction at work.
Absolutely. And by fitting the relative heights of these peaks, they could extract a quantitative measure of the non-adiabaticity, the transition probability.
How much did it vary?
A lot. For the fastest, most irreversible process, Argyros was about 0.38, meaning a nearly 40% chance of transition. For the slowest process, it dropped to approx 2022, very close to adiabatic.
Did this transition probability relate directly to whether the engine produced work?
Yes, there was a critical threshold. The theory showed that for work extraction, anaerotics and ergo had to be below a certain limit. which depended on the temperatures and the compression factor.
And experimentally.
Experimentally, they found that if they ran the engine too fast specifically, below about tau and 200 mergals, the transition probability was too high. The quantum friction generated too much entropy, and the average work output actually became negative. They were putting work in just to run the cycle.
So speed has a definite thermodynamic cost here. How did they quantify the performance loss?
They used the concept of efficiency lag, dollars NOS, defined simply as the difference between the ideal Carnot efficiency and the actual measured efficiency, 1-all-text Carnot.
And could they relate this lag to the underlying quantum processes?
Yes, beautifully. Their analysis showed that this efficiency lag LR is directly proportional to the relative entropy between the actual quantum state achieved after the finite time stroke and the ideal thermal state you get in a perfectly reversible, infinitely slow process.
So the efficiency loss is literally quantified by how far the system's actual evolution deviates from the ideal frictionless path due to those non-adiabatic transitions.
Exactly. Entropy production equals efficiency loss, tied directly to the quantum dynamics.
What about optimizing the engine? Did they find a best operating point?
They looked for the point of maximum power output. This wasn't at the slowest time, highest efficiency, or the fastest time, negative work. It occurred at an intermediate driving time, around tau approx 310 UDL.
A trade-off, as usual.
The usual power efficiency trade-off. At this maximum power point, the measured efficiency was about 2 and approx 42%.
How does that compare to the theoretical limits?
It's remarkably close to the theoretical auto efficiency, 1 omega, 1 L%, for their compression factor 3 approx $1.88, which is about 44%.
So even when optimized for power, the engine operates very near the standard auto limit, and the deviation from Carnot is significant, mainly due to that quantum friction.
That's the main conclusion from the experiment. It fully characterized the irreversibility arising from finite time driving, showed how it leads to an efficiency lag, and demonstrated that these quantum fluctuations, the non-adiabatic transitions, are what ultimately limit the power output. Quantum friction is the key bottleneck in this real-world quantum engine.
Okay, let's try to synthesize this. We've got the generalized theory from Aguilar and Lutz and the experimental validation from Peterson et al. What's the big picture?
The big picture is unified, but also highlights a central tension. The theory gives us the rigorous mathematical foundation. It confirms that correlations are a quantifiable entropic resource, delta sigma.
Right.
And exploiting this resource, delta allows quantum engines, in principle, to operate in a thermal regime and surpass the standard Carnot limit. But the experiment provides the stark reality check. While the theory allows for this advantage, realizing it in practice is incredibly hard because of finite time operation. The very act of driving the engine quickly enough to get useful power generates quantum friction.
And that friction actively works against the goal, right? It produces entropy, increases sigma, and therefore makes delta sigma less negative or even positive.
Exactly. The simulation showed this effect very clearly. The thermal advantage collapsed after just a few cycles because the accumulated quantum friction overwhelmed the initial resource. The engine gets forced back into the standard auto regime.
So the potential is there, but it seems inherently transient or difficult to maintain. The researchers themselves suggested ways around this, didn't they?
They did. Two main paths forward. One is to try and actively suppress the entropy production during the driving strokes. There are techniques for this, known as shortcut to adiabaticity protocols.
What are those?
They're cleverly designed, often complex driving protocols that force the system to evolve rapidly between initial and final states, as if it had undergone a slow, adiabatic, friction-free process, but in a much shorter time. It's like finding a quantum shortcut that avoids generating friction.
Tricky engineering, I imagine. What's the second path?
The second idea is resource replenishment. If you can't completely stop the friction, maybe you can continuously refill the entropic tank. Find a way to rapidly rethermalize or reprepare the system into a highly correlated state at the beginning of each cycle, faster than the friction depletes it during the cycle.
So either eliminate the friction or constantly refuel the correlation resource.
Basically, yes.
Okay, let's leave our listeners with a thought then. We're thinking about practical nanoscale machines. They need to run fast to be useful. The experiment showed the thermal regime collapsing quickly due to friction. The theory suggests options like shortcuts or refueling. So for you, the listener, consider this. Beyond just optimizing efficiency or power in the traditional sense, what specific engineering criteria will be vital? What new metrics might we need to successfully maintain that negative delta sigma? How do we design a continuously operating device that truly harnesses these non-classical advantages from correlations, treating them not as a fleeting boost, but as a constantly managed quantum fuel source?
Yeah, it probably requires thinking about information flow and correlation management as core engineering parameters,
Hmm.
right alongside energy and heat. It's a fascinating challenge.